Good afternoon, my dear students. My name is Dr. KCH Apparao, working as an associate professor in Mechanical Engineering Department. Okay, in previous class we discussed the question bank problems which are based upon mainly LMTD method. So in this class you will see questions which are given in question bank which are related to mainly on NTU method. Okay. So by using NTU method for both parallel flow and counter flow, we will see some numericals. Okay. So these are the formulas, you know that one, which are derived in previous classes also. Effectiveness formula for parallel flow heat exchanger. Effectiveness is equal to 1 minus exponential of minus n into 1 plus c by 1 plus c. So this is the formula, you know that n is the NTU. NTU is equal to UA by C minimum. You know this one. Okay. C is nothing but C minimum by specific heat of minimum C by C max. You know these formulas. Okay. By using this formula, we will solve the numericals. This is the formula for effectiveness, for finding effectiveness for counter flow heat exchanger. 1 minus exponential of minus n NTU, n or NTU both are same, minus n into 1 minus c by 1 minus c into exponential of minus n into 1 minus c. So this is the formula. By using this one, we will solve the numerical. So first numerical we will see, which is related to parallel flow heat exchanger. So a parallel flow heat exchanger is used to cool 4.2 kg per minute. So convert into kg per second. So 4.2 by 6, 4.2 by 6 kg per second. So this one is the used to cool of hot fluid. So this one is the mass flow rate of hot fluid, mH. This is the value. And the specific heat of the mass flow rate. So Cph is equal to 3.5 kilojoule per kg. So it means 3.5 into 10 cube joule per kg Kelvin. Okay. So this hot fluid enters at temperature. It means Thi is equal to 130 degrees Celsius. Okay. Next, a cooling water. The specific heat of the cooling water. You know that CP waters, CPC. Specific heat of the cooling water 4180 or 4.18 kilojoule per kg Kelvin or 4180 kilojoule per joule per kg Kelvin. Okay, is used for cooling purpose at a temperature. It means cold fluid inlet temperature is equal to 15 degrees Celsius. Here we know only two temperatures, only inlet temperatures of hot fluid and cold fluid have been given. Okay, so we don't know the out fluid, so outlet temperatures. So in this case, we have to use the NTU method instead of LMTD. Okay, so for solving the numerical based upon the LMTD, we should require 4 temperatures: hot fluid inlet outlet, cold fluid inlet outlet. Without these 4 temperatures, we can't solve the numerical based upon the LMTD method. So this is the drawback of LMTD, which was already discussed in previous class also. Here only if the inlet temperatures are given, then we have to choose the NTU method for finding the rate of heat transfer of heat exchangers, given heat exchanger, either parallel or counter flow. So these are the given data. Only inlet temperatures are given, 15 degrees Celsius. Okay. Then you have to find out the outlet temperatures of the liquid and outlet temperatures of the water. So we have to find out T C naught and T H naught values. So these are the solving parameter. Overall heat transfer coefficient also given, that is the 1100 watt per meter square Kelvin. So this is U. Area also given, area of the heat exchanger is equal to 0.30 meters square. So all the values given. Then you have to find out the Tc naught and Th naught. Okay, we will see how to solve these parameters. We will see once again the data which was given in the numerical. Mass flow rate of hot fluid, that is mH, 4.2 kg per minute. So that is nothing but 4.2 by 60 kg per second. This is the value. Similarly, specific heat of the hot fluid, CPH, that is 3.5 kilojoule per kg Kelvin. It means 3.5 into 10 cube joule per kg Kelvin. Okay. So these are the data related to hot fluid. Now we'll see cold fluid. So water, specific heat of the cold fluid. So this is cold fluid. Okay. Water. So CPC, you know that value, specific heat of water 4180 or 4.18 kilojoule per kg Kelvin. So it has been given, convert into joule per kg Kelvin. So 4180, you know this. Then temperatures, inlet temperatures of water Tc is equal to 15 degrees Celsius. Okay, mass flow rate of cooling water, MC also given. So MC is equal to 17 kg per minute, convert into second, 17 by 60 kg per second. So these are the values. Overall heat transfer coefficient also given and area also given. Okay, so these are the just given data. Now we'll see how to find out the outlet temperatures of hot fluid and outlet temperatures of the cold fluid. Okay, solution will see. Capacity rate. Capacity rate means specific heat. Capital CH is equal to MH and CPH. So you know this value. MH value, mass flow rate of hot fluid, that is 0.07 into specific heat of the hot fluid, that is 3.5 into 10 cube. So this is the, then you can find out the CH value. CH value is equal to 0.07. No, CH is equal to this one, 245 watt per Kelvin. Okay. Now we'll see, now we will find out the CC, capital CC, specific heat of the cold fluid, MC and CC. You know that MC is equal to 0.28 into CC, specific heat 4180. Then this value is equal to 1170.4 watt per Kelvin. So compared to CC, so if you compare the CC and CH is less than the CC, because CH value is equal to 245 only, but CC value is equal to 1170. So by then you can rewrite like this one. So CH is the minimum, means so you can represent this one C minimum. C minimum is equal to 245 watt per Kelvin, and the C maximum, CC is nothing but C max, that one 1170. Okay, watt per meter Kelvin. Then you can find out the C. C is equal to C minimum by C max. Okay. Then you have to find out the, for finding effectiveness, then you have to find out the NTU. NTU, nothing but you can represent this one N also. N is equal to NTU is equal to UA by C minimum. U value has been given, A value also given. Then you can substitute those values. U value is equal to 1100 by area 0.03. So you can find out the N value by using this C minimum and N value, NTU value, you can take the effectiveness value from the graph. Otherwise, you can find out the effectiveness. So this is the counter flow. You know that formula for the effectiveness. So this is the parallel flow. So this one is the parallel flow. So then effectiveness formula is this one. You can use this formula. Otherwise, you can use the data book to take the effectiveness with respect to NTU value and C minimum value. Okay. So this one is the formula, that is effectiveness is equal to 1 minus exponential of minus n into 1 plus c by 1 plus c. Okay. So you know that value of NTU is equal to, we already just solved that one, UA by C minimum. Okay. Then C value, C minimum by C maximum value. Okay. So if you substitute those values, okay, so substitute those values, then you will get the effectiveness value. By using the effectiveness value is equal to nearly, what is the value of effectiveness? Effectiveness value is equal to 0.64. You will get 0.64 either by data book or by this formula. Okay. Then you have to find out the outlet temperatures of hot fluid, outlet temperatures of the cold fluid. So for this one, you will see, you know that formula, effectiveness is equal to rate of heat transfer, actual rate of heat transfer by maximum possible rate of heat transfer. You know this formula. So maximum possible heat transfer means C minimum into hot fluid inlet minus cold fluid inlet. So you know that this formula we already discussed in previous classes. Based upon the previous classes, just I'm writing. So C minimum. What is the C minimum? C minimum is equal to CH value. Okay. CH is equal to 245. C minimum is nothing but CH. So with respect to hot fluid, what is the actual rate of heat transfer? That is nothing but CH, capital CH, into hot fluid temperature differences. Hot fluid inlet minus hot fluid outlet. Okay. So CH will be cancelled. Then effectiveness is equal to hot fluid inlet minus hot fluid outlet by hot fluid inlet minus cold fluid inlet. Okay. You know that cold fluid inlet temperatures. Here also hot fluid inlet temperatures. Effectiveness value also you know that 0.64. So by using this formula, you can find out the hot fluid outlet. So then hot fluid outlet, so that is nothing but TH0 is equal to 56.4 degrees Celsius. This one. Okay. So if you know this one, then you can find out the cold fluid outlet temperature. So for this one, you know that formula. So what is that? Energy equations formulas. These formulas are Q is equal to capital CH. Q is equal to capital CC into hot fluid outlet minus cold fluid outlet minus cold fluid inlet is equal to capital CH into hot fluid inlet minus hot fluid outlet. Okay. So then you can equal this one, that from which you have to find out the TC0. Then TC0 minus TCA is equal to capital CH into hot fluid inlet minus hot fluid outlet by CC. Okay. Then you can send minus TCA. Then TC0 is equal to, so this plus TCA. So you know all the values. Capital CH 247, I think value. That value is equal to 245, and this value already we derived this one. Okay. So CH and capital CC. So this is C maximum. This one is the C minimum also. This is the C minimum. CH is nothing but C minimum. This one is the C maximum. We already derived these values. solved this value. If you substitute these values, C minimum or CH value, and hot fluid inlet, you know that hot fluid outlet also we already solved that one, 56.4, and the cold fluid inlet, you know this one. If you substitute all the values, you will get the T C naught value. So the T C naught outlet temperature of the cold fluid is equal to 30.4 degrees Celsius. So this is the value. So in this way, just you can solve the unknown parameters by using the known parameters based upon the effectiveness method. Okay. So here already given, we solved this one. Okay. So final temperature is equal to 30.4. Now we'll see one more numerical. A counterflow heat exchanger is used to cool 2200 kg per hour. So here also kg per hour you can convert into kg per second, 60 into 60. Okay, kg per second of oil. Specific heat of the oil also given. So this is the mH and CPH, specific heat of the oil, 2.5 kilojoules means 10 cube joule per kg Kelvin. Okay. So next to water. So this is the oil entering of the oil. So THI is equal to 100 degrees Celsius, and TH0 also, you know this one, 35 degrees Celsius. By using the water entering temperature TCA, that is 17 degrees Celsius. Okay. If the overall heat transfer coefficient is exposed to 1.5 kilowatt per meter square. So it means rate of heat transfer has been given, that is 1.5 kilowatts means 1.5 into 10 cube watt per meter. So this is not. So this is the overall heat transfer coefficient U. U is equal to overall heat transfer coefficient is 1.5 into 10 cube watt per meter square Kelvin. So these are the values given in this numerical. Make calculations for water flow rate. Water flow rate means mass flow rate, MC, we have to find out. Next, surface area required, area of counterflow, we have to find out. Next, effectiveness of heat exchanger also, epsilon. Effectiveness, we have epsilon. Effectiveness also you have to find. So these are the parameters you have to find out. Okay, we should find out. Next, exit temperature of water is not exceed. Exit temperature means hot fluid, cold fluid outlet also given, that is the 85 degree Celsius. Use NTU approach, because here hot fluid inlet and outlet and cold fluid and inlet and outlet. So 4 temperatures: hot fluid inlet and the hot fluid outlet, cold fluid outlet and cold fluid inlet. 4 parameters of temperatures. We know all the 4 parameters of the temperature. Then we can use the LMTD method, because if you know that 4 temperatures, inlet temperatures of hot, inlet and outlet temperatures of both the fluids, then you can use the LMTD method. But here, so it was specified that we have to use the NTU method. By using NTU method, we have to solve this numerical. Okay. Now we'll see. Okay, how to solve it. So we already discussed the given data, what was given in the numerical. Then first you have to find out the Q value, rate of heat transfer, because you know that energy equations is nothing but Q is equal to mHch into THI minus TH0. So hot fluid temperature differences into specific heat. Similarly, MCCC, TC0 minus TCA. Okay. Mass flow rate of water given 20 to 220. Okay, something. So 2200 uh, should be converted into 2200 kg per second. 2200 by 60 into 60. Then specific heat of the oil, hot fluid specific heat, that was given 2.5 kilojoule, 2.5 into 10 cube kilojoule per kg Kelvin. Next to temperatures, hot fluid inlet 100, hot fluid outlet 10, 35. So the is equal to mass flow rate of the cool fluid. We have to find out this one, MC. CC, you know that value, specific heat of the water, that is 4180. Then you can write that one in kilojoule per kg Kelvin. Okay. So cold fluid outlet 85 degrees, cold fluid inlet to 17 degrees. Okay. So by using this formula, you can find out the mass flow rate of water. Okay. So all the parameters we know except MC. Then you can find out the MC. Okay. Then we have to find out the effectiveness. One was completed according to numerical. That one is the MC, mass flow rate of the cold fluid, computed. Next you have to find out Q. Q is equal to, you know, this one MH and CH into THI minus TH0. So all the values given, you can find out the Q value also. So that Q is equal to here also. You can find out this is the Q. Okay. Then we have to find out the effectiveness. For effectiveness, we should understand specific heats, which is minimum, which is maximum. It means, so C minimum we have to identify and the C maximum we have to identify. So for this one, just to find out the CH is equal to MH into CPH. Similarly, CC, specific heat of the cold fluid, is equal to MC into CPC. We know all these parameters, then you can find out the CC, that is the value of this one, CH is the value of this one. So compared to CC, CH is minimum, not minimum, maximum. Okay. So by comparing these two, we can understand CC, specific heat of the cold fluid, is the C minimum, and CH automatically, that one is the C maximum. Okay. This is C minimum. Then you know the formula that C value, C is nothing but C minimum by C maximum. C is equal to C minimum by C max. So C minimum by C max, so that is nothing but 1.046. Then you have to find out the effectiveness. Effectiveness means effectiveness is equal to actual heat transfer by maximum possible of heat transfer, Q max. Q max means that is related to so less is CC. CC is less one. So we have to consider the rate of heat transfer with respect to cold fluid. Cold fluid formulas, that Q, rate of heat transfer, is equal to Q by Q max, Q by Q max, because CC thermal so Q by Q max, Q is equal to MC and CC into TC0 minus TCA. MCCC is nothing but capital CH, capital CC. Capital CC is nothing but C minimum by C minimum into hot fluid inlet minus hot fluid outlet, cold fluid inlet, cold fluid inlet. Okay, so this will be cancelled. Then automatically this is the TC0 minus TCA. Okay, so then THA minus TCA. If you substitute these values, then you will get the effectiveness value. Effectiveness is equal to 0.783. Okay. So in this way, just you can solve the numerical. We will see one more numerical, then we will conclude this one. A home air conditioning system uses a counterflow heat exchanger, so that cools 0.8 kg per second. So it has been given in kg per second of air from 45 degrees to 15 degrees. Okay. So arrangement is counter fluid exchanger. Hmm. Okay. Next, the cooling is accomplished by the steam of cooling water that enters the steam. Mass flow rate of the steam also given 0.5 kg per second. Air mass flow rate of the air, it has been given. Next to it enters the 8 degrees Celsius. Okay. So here air and steam, two parameters, two fluids. With the overall heat transfer coefficient also given 30, that is the 35 watt per meter square Kelvin. So what heat exchanger area is required? Use effectiveness NTU method. Okay. So by using the effectiveness, you can find out the area of this counter fluid exchanger. So first of all, you have to find out the specific for NTU method. One thing you should know that for approaching NTU method, C, you have to identify the C minimum and C maximum. So for this one, you have to find out the CH and CC. CH is equal to MH CPH. CC is equal to mass flow rate of the cold fluid into specific heat of the cold fluid. Okay. So thermal capacity of hot fluid. So here hot fluid is equal to air, cold fluid is the steam. Okay. Or water enters. Cold fluid is water. So that is the steam, nothing but air and water. So mass flow rate of the air also given, that is a 0.8. Specific heat of the air also given, that one. Okay. Then you can take this 1005 specific heat of the air. So from the data book. Okay. So by using this one, you can find out the capital CH. Capital CH is equal to MHCH 0.8 into 1005. So the value of this one is equal to 804 kilojoule per kg. This one. Then you can find out the CC. CC is nothing but specific heat of the water. So mass flow rate of the water that has been given, that is 0.5 kg per second. So 0.275. So 75 has been given. Then specific heat of the water CC, that is nothing but 4186 or 4180. We can take anyone. Then CC value is equal to 3139.5. So this is 8804. This one is the 3000. So compared to both, then you can understand CH is C minimum and the CC is the C max. Okay, then if you know that C minimum and C maximum, then you can find out the C. C is nothing but capacity ratio C minimum by C maximum. 804 by 3139.5 is equal to. So capacity ratio C is equal to 0.256. Then you can find out the effectiveness. Effectiveness formula, you can use that direct formula, NTU method formula. Otherwise, you can use this one also. Effectiveness is equal to, with respect to C minimum. C minimum is which one? So C minimum is equal to hot fluid. Okay, specific heat of the hot fluid. So the actual rate of heat transfer with respect to hot fluid by Q max. Okay, so for based upon the C minimum, CC into hot fluid inlet minus hot fluid outlet by Q max means so C minimum into inlet temperature THA minus TCA. Okay. So C minimum, CH both are same. You can cancel this one. So THA minus TH naught by THA minus TCA. So by using this formula, you can find out the effectiveness. Okay, all the temperatures are given. Then if you substitute these values, you can find out the effectiveness. Okay. So here, otherwise you can find out the effectiveness by using this formula also, 1 minus exponential of minus n into 1 minus c by 1 minus c into exponential of minus n into 1 minus c. Okay, so this is the formula for counterflow heat exchanger. So then if you substitute all the values, so n is nothing but UA by C minimum. You know that C minimum and A and U also, overall heat transfer coefficient. Then by using this one also, you can find out the effectiveness. If you know the effectiveness, you can find out the area also. Because, okay, here we don't know the area. So it means we should find out the effectiveness by using this formula. So if you know that effectiveness formula, then by using this formula, what is that formula? So no need of this one also. If you know this effectiveness, then you can find out the area. Area is equal to, by using this one, you can find out the effectiveness. Effectiveness is equal to UA by C minimum. C minimum. But NTU is the UA by C minimum. You should, we don't know the area. So we have to use this formula, effectiveness formula, Q actual by Q max. Okay. Then you can find out the area. Area is equal, effectiveness is equal to UA by C minimum. Then you have to find out the area. Area is equal to effectiveness into C minimum by U, overall heat transfer coefficient. Okay. If you substitute the values of effectiveness, what is the value of effectiveness? Effectiveness value is equal to, already solved that one. That value is equal to 0.81. So 0.81 into overall heat transfer. C minimum is equal to 804 divided by overall heat transfer coefficient, that is 35. Then the area is equal to, that is the value. The area is equal to 44.10 meters square. So in this way, just we can solve the different numericals which are based upon the NTU method. Okay. So these are the textbooks for the reference I have given. We can refer these textbooks for more numericals or more problems based upon the NTU method. So thank you for listening this class.
Like, share and subscribe. Hit the bell icon for more updates.
One comma, 2 comma, 3, start. Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in a mechanical engineering department. Okay, we are discussing the question bank questions, critical thinking questions, next to different numericals also. In this class, I would like to explain about the cross flow heat exchangers. What are the numericals which are related to cross flow heat exchanger? Next, how to find the it means rate of heat transfer in cross flow heat exchanger. We will see this one. We will see what is cross flow heat exchanger first of all. What is the difference between the counter flow heat exchanger and cross flow heat exchanger? We know that in cross flow heat exchanger, flow is perpendicular to each other. In this one also, heat transfer takes place between only two fluids. You know this one, but in parallel and counter, the flow direction is parallel to each other. But in cross flow, the flow direction is perpendicular to each other. Okay. So if the heat exchanger other than the double pipe type is used, okay, the heat transfer is calculated by using the correlation factor. So this is very important. If the heat exchanger other than the double pipe heat exchanger, it means the double pipe heat exchanger other than double pipe heat exchanger means we will use the cell and tube type heat exchangers. So in this cell and tube type, we will see the uh, cross flow of fluids, hot and cold fluid. We will see. Okay, the heat transfer is calculated by using correlation factor. So this one is very important. That is represented by F. F is very important. So correlation factor is applied to LMTD, only for LMTD, for a counter flow double flux arrangement. It means so cross flow, for the cross flow heat exchanger also we use the same setup or same formula of counter flow heat exchanger, including the correction factor. Okay. So with the same hot and cold fluid temperatures what are taken in the cross flow, it means counter fluid exchanger. Here also you take the same temperatures, all are same, except you have to add the F correction factor for the counter fluid exchanger. If you add this correction factor, it means you know that the rate of heat transfer formula for counter fluid exchanger, UA into delta T LM. Okay. So if you add this one, Q is equal to F into UA delta T LM. So this formula belongs to cross flow heat exchanger. Okay. So this F is nothing but a correction factor. So UA F into delta TLM. F is the correction factor. Here delta TLM formula, you know that one, delta T1 minus delta T2 by ln of delta T1 by delta T2. Same formula. Okay. But delta T1 is equal to, so delta T1 is equal to same set of hot fluid inlet minus cold fluid outlet. What was seen in counter fluid exchanger. So same formulas. Delta T2 is equal to hot fluid outlet minus cold fluid inlet. Okay. So same formulas, same setup. Okay. Same arrangement. What was taken in counter fluid exchanger. Here also we'll take this one. So along that one you have to add the correction factor. F. Okay. Okay. How to find F? We'll see that one also. Then if you know that F value, then you can use the formulas of counter fluid exchanger. Then you can solve the numericals, rate of heat transfer in the cross flows. Okay. The values of correction factor F according to the reference flow is plotted in the different areas. So 10 to 8 to just these are the figures which are given in the data book. By using those figures, you can find the, or we can take the F value from the figures. Okay. So for several conditions also here given here for several different types of heat exchangers. Okay. We'll see first of all. So this one already explained this one. This is very similar to counter flow heat exchanger except F correction factor. If you add this correction factor to the formula of counter fluid exchanger, then it will become the formula of cross fluid exchanger. Okay. So Q is equal to UAF into delta TLM. Delta TLM is equal to similar to cross flow, so equal to cross fluid exchanger. Hot fluid inlet minus cold fluid outlet, hot fluid outlet minus cold fluid inlet by, so delta T1 by delta T2, same formulas. Okay. We'll see the graph, first graph. The condition is correction factor plot for exchanger, heat exchanger with one shell pass, 2 or 4 or any multiple of tubes. It means so tubes are multiples, but one cell, multiple tubes. So how to take this diagram, this figure, then you can find out the correction factor F value with respect to P and R constants. We'll see what is P and what is R. So how to find out the P and R with the temperatures which are given in the numerical. Okay, you will see. So this is the first figure. This is the figure which is related to the setup, only one cell and multiple tubes. Okay. So this one is the 2 cells and multiple tubes. 4 or 8 or any multiple tubes and 2 cells, cell 1 and cell 2. So for this one, for this condition, so you have to choose this diagram. By using this diagram, you can find out the correction factor F value. So this one is the single pass cross fluid exchanger. Here both the fluids unmixed, both the fluids unmixed. Okay, so if the both the fluids are unmixed condition, then you have to take this uh, figure. Okay, so one more, one fluid is mixed, another one is unmixed. Okay, for this one fluid is mixed, other one is unmixed, then you have to take this figure. So based upon the condition, you have to take the figure. Based upon those figures, we can find out the correction factor value by using the R value and P value. How to find out R and P, what is the formulas of those, we'll see. Okay, so in this numerical, just we will see. Water at the rate of 68 kg per minute is heated from 35 to 75 degrees Celsius by an overall by an oil having this specific heat. Specific heat of the oil also given. Temperature inlet and outlet also given. Hot fluid inlet, hot fluid outlet. Mass flow rate, specific heat. So all the values are given. So M water means cool fluid. So MC, you know that CC also given. TC not also given. TCA also given. Okay. So MC, so that is nothing but 68 by 60 kg per minute into specific heat. So specific heat of the you know the specific heat of the water 4180 into cold fluid outlet 75 minus 35. So by using this one, you can find out the Q value. Okay, so that the value is equal to 189.5 kilowatts. Overall heat transfer coefficient also given. Next to another fluid is oil, hot fluid. Hot fluid entering temperature also given 110 degrees Celsius and leaves 75 degrees. Overall heat transfer is 320. Okay, so calculate the heat exchange area. Next to total heat transfer is determined. So this numerical is already solved in LMTD method. So we can find out the area. So for this one, you have to find out the delta TLM. So this is the what type of heat exchanger. This one is the counter fluid exchanger. Okay, so counter fluid exchanger. Then you have to take the formulas. Hot fluid inlet to cold fluid outlet. Hot fluid outlet to cold fluid inlet. Okay, so by using this one, you can find out delta T LM is equal to 37.44. Okay, so you know that Q is equal formula UA into delta T LM. U already we solved that one. The value is equal to U 189. So this is 189.5. Overall heat transfer coefficient also given. So what is the value of that one? 320. So this is 320 into area into delta TLM. What is the area of delta TLM value? 37.44. So by using this formula, you can find out the area. So that area is nothing but this one. Okay. So this numerical is extended so that instead of the double pipe heat exchanger of example 1, it is desired to use shell and tube heat exchanger. Okay, shell and tube heat exchanger. So one cell, multiple tubes. You have to take that formula figure also. So with the water making one shell pass and oil making the two tubes. 2 tubes or 4 tubes or many tubes. So one cell, multiple tubes. Then based upon the condition, you have to take that figure for finding the correction factor. Okay. Calculate the area required for this heat exchanger, assuming the overall heat transfer coefficient remains at 320 degrees Celsius. Same setup. Okay. So then we have to add the correction factor F. Correction factor F. So we have to find out the F value. So for this one condition is one cell and multiple tubes. Multiple tubes. So by using the data book, you can take that to diagram. By using that diagram, you have to find out the F value. Okay. So for finding F value, you have to find out the R and P. So these are very important. By using this R and P, then you can find out the F value. Okay. So P. So what is P? P is equal to TC naught cold fluid outlet minus cold fluid inlet by same inlet temperature differences. Hot fluid inlet minus cold fluid inlet. Okay. So cold fluid temperature difference by inlet temperature differences. That is the P value. Similarly, R is the hot fluid temperature differences by cold fluid temperature differences. Hot fluid temperature differences. This is the cold fluid temperature differences. Okay. So by using this R and P, then you have to find out the F value by using that. What is the figure? The figure which is related to one cell and multiple tubes. You know that we'll see that that is the figure. This one cell and multiple tubes. Okay. So by using this one, you can see. So this is the P value. This is the R values. The R values. Okay. These are the graphs. By using this R values and P values, you can take that F value. Okay. So suppose R is equal to 3 and suppose P is equal to 0.4. Okay. So R is equal to 3, 0.4 or 0.25. So suppose this is the value. Okay, in this way, just like we have to find out the F value with the uses of by using the P and R values. Okay. Okay. So by using this P and R values, F is equal to 0.8. F is equal to 0. So by using this F value, you can find out the Q. So Q is equal to, you know that already rate of heat transfer, same rate of heat transfer. Q is equal to UA into F into delta TL. Okay. You know that F value, you know that U value, you know that F value, Q value also. Everything you know that. We have area, you have to find out. Area is equal to Q by UA into U into F into delta TL. If you include the F, what is the area? We have to find out. That area is equal to 19.5 meters square. So this is the numerical which is related to cross flow. Okay. We'll see one more numerical which is related to cross flow. A heat exchanger like that that shows the here figure also given is to heat an oil in the tubes. Specific heat of the oil also given 1.9 kilojoule per kg Kelvin from 15 degrees Celsius to 85 degrees Celsius. Okay. Heating an oil. So blowing across the outside of the tubes is the steam. Steam and oil. Okay. Steam enters. Entering steam is THA is equal to 130 degrees Celsius and leaves at 110 degrees Celsius with the mass flow rate of so mass flow rate of the steam also given 5.2 kg per second. The overall heat transfer coefficient is equal to 275 watt per meter square degree Celsius. So for this steam, so this one specific heat of this steam also given. That one is 1.86 kilojoule per kg. Okay. So calculate the surface area of the heat exchanger. So here you have to find out the surface area of the heat exchanger. So first of all, you know that the condition, what is the condition? So one blowing across outside of the tubes enters the pipe. Based upon the figure, you can understand what is the condition, either two cell or one cell or multiple tubes. Okay. So first of all, we find out the Q value. Q is equal to MH and CH into hot fluid inlet minus hot fluid outlet is equal to MCCC into cold fluid outlet minus cold fluid inlet. So this is the formula. So steam mass flow rate of the steam has been given, and specific heat of the steam also given, and temperatures of the steam temperatures inlet and outlet, that is 130 and 110. So that one also given. So it means MH and CH and delta TH. So these values given. By using this one, you can find out the Q. Okay. So for the steam, all the mass flow rate value and the specific heat of the steam, inlet and outlet temperatures of the steam. So that is the hot fluid. So those values given. By using those values, you can find out the Q value. Then by using this Q, you know the formula for the cross flow use Q is equal to UA into F into delta TLM. Delta TLM you can find out by using the temperatures, because inlet outlet temperatures of hot fluid and cold fluid both are given. Okay, so then you know that value of Q, and U value, overall heat transfer coefficient, also given. Then you can find out to first F factor. By using this F1, you have to find out the area. So identifying F value, so that is very important. Okay, so the figure, by using that figure by arrangement, so here figure is not given. So by using that figure, you can take F value by the help of data book. F is equal to, that value is given 0.97. If you know that F value, then you have to find out the, because by using the P and R values, you can find out the F value. Okay. Then you have to find out the delta TLM. If you know the delta TLM, then you can substitute all the values. Q is equal to UA F into delta TLM. Then area is equal to Q by U F into delta TLM. Okay, if you substitute all the values, Q value is equal to 193.000000 by overall heat transfer coefficient and F value and temperature difference values. Okay, then area is equal to 10.82. So this is the numerical. So these are the textbooks for the reference I have given. You can refer more for solving the more numericals which are based upon the cross flow. So thank you listening this class. Thank you.
నేను వేస్తే 4
మూడే సార్.
ఓహో మీరు 20 నిమిషాల కంటే ఎక్కువేనా చేస్తున్నాను సార్.
నేను వాచ్ తేక కష్టమైపోతుంది సార్.
ఓకే ఓకే
వాచ్ ఆగిపోయింది ఒకసారి వర్షంలో తెలిసి.
మొబైల్లో చూసుకోదా?
ఆన్లైన్ ఉన్నట్టుంది.
అవునా? 4 hours ఉంది సార్.
అంటే 50 minutes అయినట్టుంది అంతే సార్. 50 minutes అయినట్టుందండి.
లేదు మీకు 1 hour దాటింది.
5 hours లో ఉన్నదంట. లాగేసండి, ఇంకో 2 ఉన్నాయి, ఇంకా చాలా ఉన్నట్టున్నాయి.
ఇప్పుడు మళ్ళీ మీ దగ్గర ఇప్పుడు తయారు చేస్తాను.
నేను ల్యాప్టాప్ తెచ్చుకోలేదు సార్.
అయ్యో
తప్పు చేశాను.
తెచ్చుకోవాల్సిందే.
అంటే మధ్యాహ్నం అంటే వాళ్ళు కట్టేసి వెళ్ళిపోతారని ట్రై చేస్తున్నాడు.
ఓకే ఓకే, 50 చెప్పాను, 51 చెప్పానా?
తెచ్చాను.
రంజిత్ కుమార్ గారు
ఇంకొక 2 తెచ్చేసుకుంటే.
హలో సార్, వస్తారు 1 గంట తర్వాత.